Hello everyone. In this video, we're going to go over the test review for midterm 4. That covers chapters 6 and 7 in our textbook. I will note that this review is longer than the test. That's on purpose. You can practice more skills. The test is timed hopefully pretty well to give you time to complete it within the allotted time. Now, let's start going through problems. First off, I have you solving a nonlinear system. Couple things to remember is sometimes it's good to think of this graphically. If you haven't seen this before, an x squared plus y squared equals a number equation, the graph of this is actually a circle centered at the origin. And this is a line. So I'm going to draw a very rough graph. Oh, darn. My circle drawing's so poor, even Microsoft doesn't recognize it. So here's a circle, and here's a line. So we should expect there to be two solutions. Sometimes with a line and a circle, a line will lie tangent to the circle, so there could be one, or the line will be outside the circle, so there could be zero, but most likely there will be two. So we can do this either through substitution or elimination. I don't have any matching variables. The second equation is all in x, and the first equation is all in x and y squared. Excuse me, everything's x and y here to the first power. So I'm going to try substitution. Specifically, I'm going to solve this second equation for y. And so if I solve that for y, I'm subtracting 7x from both sides. So I get y equals negative 7x. And so I'm going to take that y and put it in for the y squared here and solve that equation in terms of x. So this turns into x squared plus negative 7x parentheses squared equals 800, and negative 7x squared, I have to square both of them because they're multiplied together, so that gives me 49x squared. So remember, when you square a negative, it becomes positive. Well, now I have like terms here on the left-hand side of my equation, so I end up with 50x squared equals 800. I'm going to divide both sides by that 50, and I end up with x squared equals 16. Well, hopefully you see that I made this kind of nice because 16 is a perfect square. So I'll square root both sides to get my final x answer. Now I'm going to do something a little Dora the Explorer style, where I'm going to write something and talk to you as if you're going to respond. So I've made an error right here. Well, two errors. First, the square root gets rid of the squared. But look at this. There's actually a small error in this solution here. Do you know what it is? That's right. I forgot the plus or minus. Whenever we take a square root of both sides, we need a plus or minus because every number has two square roots, a positive square root and a negative square root, because the negative, if you square a negative, it becomes positive. Now, what does that mean for my solutions? I have two of them. For one of them, x equals 4. Well, we know y equals negative 7 times x, in this case 4, so I get negative 28. So one solution is 4 comma negative 28. Similarly, I'm going to put in x equals negative 4. So negative 7 times negative 4 equals positive 28. And so that gives me my other solution of negative 4, positive 28. And looking at our graph, that 4 negative 28, that tells us that instead of having a line going upward through my circle, it looks like I have a line going like this, and that 4, negative 28 is down on the right, that negative 428 is up on the left. All right, now let's do a 3-variable one. Now, in this chapter, you were introduced to solving 3-variable equations with matrices. Now, you may wonder, why the heck do we do that? The matrices look so fake. The reason is computers. Computers love matrices. Any sort of computer operation is likely done using matrices. And so, if you have any interest in going into some sort of programming, you'll probably want to get comfortable playing around with matrices. So here, I have taken that system and written it in its matrix form, augmented matrix form. Remember, we can find the inverse of the matrix, but that's often kind of tricky with a 3x3. So I'm just going to do my normal row reduction method where I make zeros in columns. So I will start with the first column here, and I'll use row 1 to make everything else 0. So I'm going to do -2 row 1 plus row 2. And to help myself remember what those numbers are, I'll often write them on top here, because I'm taking -2 times row 1. And that helps me keep track of what I'm doing. And then I'm going to do negative row 1 plus row 3. Because remember, my goal is to change all of these first entries, other than the top one, to 0. And so I get a -1, -1, -1, -4. And so when I add this -2 to this +2 in the second row, it's going to go to 0. Exactly what I want. So I'll have 1, or my first row is unchanged, 1, 1, 1, 4. And I'll have a 0 here in the first column, second row. But everything else is going to look weird. I end up with a -3 here, a -4 here, and then a -9 here. Similarly, in the last row, I have a 0 here. I have a -3 in the second entry, a -2 here, and a -3 here. And as a reminder, that comes from adding the blue entries to the third row. Okay, now I'm going to try to make it so I have a 1 in the second row, second column, because my goal is 1s are along the main diagonal and 0s everywhere else. So I'm going to do -1/3 times row 2. And so the only thing that's changed here is row 2. So I have 0, 1, 4/3, and 3. Then 0, -3, -2, -3. And now I'm ready to zero out the second column. So I'm going to do negative row 2 plus row 1. And I'll write those numbers up here. -0 is 0. -1 times 1 is -1. I have a -4/3. And then a -3 here. And then I'm going to do 3 row 2 plus row 3. So I have a 0, a 3, a 4, and a 9 here. And I'm going to add those all together. So I'm going to have 1, 0, and let's see, -4/3 plus 1 is -1/3. And negative 3 plus 4 is 1. My second row remains unchanged because I was using that to make zeros. I have 0, 0, 2, 6. Now I'm going to follow the same pattern where I'm going to force there to be a 1 in this bottom right-hand entry. I'm going to force that to 1. And so I'm going to do 1/2 row 3. And that turns into only the bottom row changing, so I'm just going to recreate the other 2 rows. So on the bottom, I get 0, 0, 1, 3. Now let's talk about what this tells us. Remember, the way we set this up, that makes it so the first column represents X, the second one represents Y, the third one represents Z. That vertical line is an equal sign, and the right-hand side is the number of an equation. So this bottom row tells me that Z, 1Z equals 3. So I found one of the variables. And now I'm going to do 1/3 row 3 plus row 1 to get rid of that negative 1/3 there. I'm going to erase these letters here so I can write my numbers in. So I get 0, 0, 1/3, 1. Negative 4/3 row 3 plus row 2. I'll go ahead and write that down here. Oh, I apologize. I usually write this one in different colors, so I'll change this to blue. Oh, and that usually changes it. Never mind. I'll just write the results down here. So I get 0, 0, negative 4/3, negative 4. And remember, this blue one is going into row 2. And so I end up with 1, 0, 0, 2, 0, 1, 0, negative 1, and 0, 0, 1, 3, because that last row didn't change. So that looks like my answer. That tells me my answer is x equals 2, y equals negative 1, and z equals 3. Now, I highly recommend checking these problems. It's easy to make little mistakes. That's one reason why I was very careful to write down what I was doing in each step and very careful to write down the numbers I was adding. So I'm going to go ahead and check by plugging those numbers into my 3 equations. So I get 2 plus negative 1 plus 3. Does that equal 4? Yes, it does. The left-hand side turns into 5 minus 1, which is 4. So it fits the first equation. Now let's try the second equation. 2 times 2 minus negative 1 minus 2 times 3. And hopefully that equals negative 1. Let's check. I end up with 4 plus 1 minus 6. And that does, in fact, equal negative 1, because I end up with 5 minus 6. Last but not least, we check the last equation. Does 2 minus 2 times negative 1 minus 3, in fact, equal 1? Yep, because I end up with 2 plus 2 minus 3, and that definitely equals 1. Wasn't that a fun problem? So, as a reminder, I am aware of the time you do and do not have on this test. This review is longer than the test. Okay, let's look at another method of solving these equations. One of them is Cramer's rule. So Cramer's rule says that we can find the value of a variable by dividing two determinants. We do the determinant of something called ax divided by the determinant of a. Remember, a is what we call the coefficient matrix. It's where I take all the coefficients in my original matrix and just put them down. I don't augment it with the answers to the equation. I just write it down. I just write down all the coefficients. I'm going to double check it, make sure I didn't miss a negative, because that's always the bane of my existence when doing these. And I'm going to go ahead and start out by finding this determinant. Remember, the way I do that is I copy down the first two columns again, and then I multiply down along diagonals. So this first diagonal is going to give me negative 30. This second diagonal is going to give me negative 54. This third diagonal is going to give me negative 60. If I add those together, I end up with negative 144. And then I do the same thing with the diagonals going up. I'll multiply these together to get positive 60, since there are two negatives in there. Multiply these together to get 90. And multiply these together to get negative 18. And so those add up to 132. And so the determinant of A is going to be negative 144 minus 132, which is negative 276. Well, that's a fun number. All right, now let's find the determinant of AX. Now remember, AX is the matrix where we replace the X column with the output column. So the negative 6, negative 42, and 10. And then all the other columns stay the same. Negative 9, negative 10, and 10. Negative 3, 3, and 1. Then I'll go ahead and find that determinant by reproducing the first column and the second column. And multiplying along the diagonals. And remember, we always do bottom minus top. I'm going to change to a nice green here. So this first diagonal, there's two negatives, so that ends up being a positive 60. The next column, we have one negative, so that ends up being a negative 270. Then this last diagonal has two negatives, so we have negative 3 times 42 times 10, and that ends up being 1260. So I'm going to go ahead and combine those together. That ends up being 930. Oh, not 930, I apologize. I'm just going to plug it in a calculator because I'm feeling lazy. And that's the nice thing on the test is with numbers like this, you'll have a calculator you can use. These three numbers end up adding up to 1050. It's kind of a fun number for this course. Now I do the same with the upward diagonals. I have two negatives here, so that ends up being positive 300. I have one negative in this next diagonal, so that gives me negative 180. I have two negatives in this last diagonal, which makes it positive, which that means it is, I'm going to plug it into a calculator just to make sure I'm doing this right. Positive 378. Whoops, helps if I write the 300. And I'm going to go ahead and add those up. And that gives me 494. And as a reminder, I do the top minus, or excuse me, the bottom minus the top. So 1050 minus 494. And that ends up being 556. So that tells me that x is going to be 556 divided by negative 200, or sorry, 552. I apologize, I wrote down a number wrong. This 374 was supposed to be a 378. I don't know where I got that for. And so this ends up being 498. And that ends up being 552 as our determinant. And so my x value, once again, this is a reminder that you always write down your work real carefully here and check it because it's easy to make those mistakes. X is 552 over negative 276. And that actually is negative 2. Now we find y and z the same way. Now, if you feel like you have this technique down, you can skip this part of the video. But if not, I'm going to go ahead and show how to find AY and AZ to help us, to help give us more practice in doing these determinants. All right, let's find AY, or I should say the determinant of AY. So I'm going to replace the Y column with the output column. I'll reproduce the first two columns. And then I'll do my diagonal multiplication. So I multiply along this diagonal with one negative. That ends up being negative 126. The negative 6 times 3 times 2 ends up being negative 36. And the negative 3 times 2 times 10 is negative 60. So altogether, those three numbers add up to, let me plug that in a calculator real quick, negative 222. I'll do the same thing with the diagonals that go upward. I have 2 times negative 42 times 3. And I'm once again going to plug that into a calculator because I don't feel like doing that multiplication in my head right now. and that ends up being 252, positive 252, since there are two negatives there. We have 10 times 3 times 3 in the next diagonal, which gives us a 90. And then 1 times 2 times negative 6, which is negative 12. Adding those all together gives me 330. So I do my bottom sum minus my top sum. Since they're both negative, this ends up being negative 552. Y is the determinant of AY divided by the determinant of A. So that's negative 552 over negative 276, which equals positive 2. Now, this method may seem overly complicated. Some students like it because it's very straightforward. It's like the quadratic formula. You do the same thing over and over again. I'll now build AZ and take its determinant. So remember, for AZ, I'm replacing the Z column with the output column. And I think honestly what makes this problem seem really hard is that negative 42. Just gives us some big numbers. Okay, I've reproduced the first two columns, and now I'm going to multiply. So I multiply down here, and I get negative 300. I multiply down here. Since I have two negatives, that's going to be positive. I'm going to plug that into a calculator, and that's positive 756. Negative 6 plus 2 plus 10, or excuse me, times 2 times 10 is going to be negative 120. I add those together. And I get positive 336. I'll now do the upward diagonals. I get a positive 120 for that first diagonal. And then I get a negative 1260 for that second diagonal, because that's what our 10 times negative 42 times 3 is going to give us. And then 10 times 2 times negative 9 is going to give us a negative 180. I'll add those together. I end up with negative 1320. I do bottom minus top, so I'll have 336 minus negative 1320. I'm going to plug that in a calculator, and it gives me 1,656. And so Z is going to be that 1,656 divided by 276, negative 276, excuse me. And I'll plug that in the calculator. And that ends up being negative 6. So Cramer's rule is nice. It's focused on calculations more than algebra. So it's really good for computers. It's something you could program into a computer relatively easily. All right, let's practice matrix multiplication now. Matrix multiplication seems really weird, but there are a few contexts where it actually makes sense to do matrix multiplication this way, where we do the take the column and smash it down method, or whatever way you like to think of it. This actually works well when looking at prices. If you imagine that we're pricing out different quantities of items from stores. As a reminder, depending on how you look at it, when we do matrix multiplication, we take a column and smash it down over the rows. So that means that my first column in my new matrix, I'm going to do -2 times 3 plus 1 times 3, because I'm taking that 3 column and smashing it down. I'm going to have 5 times 3 plus 3 times 3. I'm running out of space, so I'm going to take this writing I made and move it over here. Just to make my life a little easier. Now I'm going to take the next column and smash it down. That next column is the -1, -2. So I'll have -2 times -1 plus 1 times -2. And then -2, or excuse me, 5, because that's my first entry of my second row in the first matrix. 5 times -1 plus 3 times -2. A good way to look at it is notice that in the first row of my new matrix, I'm using the first row of my first matrix over and over again. And then I'm using in the columns, I'm using the columns of my second matrix. For my third column in my product matrix, I'll have -2 times that 2 plus 1 times 1. So notice that 2 and 1 is the last column in our second matrix. And then we have 5 times 2 plus 3 times 1. Now, I can do this multiplication in the first place because A is a 2 by 2, 2 rows by 2 columns, and B is a 2 by 3. Remember, we need the columns of the second to match the rows of the first. That allows us to take the columns of the second and smash them down, so to speak. Now I complete all those calculations, and I end up with -3, 24, 0, -11, -3, and 13. All right, now let's find an inverse of a matrix. Remember, we only have inverses of square matrices. So I can find this inverse by using a little trick. We can also do the row reduction method. I'm going to do the trick. The trick is that A inverse is 1 over AD minus BC times D negative B negative C A. So remember, this is assuming that we name our numbers in our original matrix A, B, C, D. So in this case, my A is 6, my B is 2, my C is 5, and my D is 2. So A inverse is going to equal 1 over 12 minus 10, because 6 times 2 for AD is going to be 12. 5 times 2 is going to be our BC. Then I have 2, -2, -5, and 6. Now 12 minus 10 is just 2. So this is 1/2 times 2, -2, -5, and 6. And multiplying that 1/2 in, we end up with 1, -1, -5/2, and 3. And that's it. That's our inverse. We can always check it by using matrix multiplication. So by taking our columns and smashing them down and making sure it ends up working. All right, next let's find a determinant. We did way too many 3 by 3 determinants. Luckily 2 by 2 is easy. It's just AD minus BC. So I end up with 14 minus 24, which is -10. And that's it for this problem. Wouldn't it be great if they were all that short? All right, time to do a partial fraction decomposition. The big thing to remember with partial fraction decomposition is it all depends on the factorization of the denominator. Since this has an x minus 2 in the denominator, when I decompose this, I'm going to have an x minus 2 fraction and an x squared plus 3 fraction. Additionally, the numerator of these partial fractions will be 1 degree lower than their denominator. So I have a linear here, so I'll have just an a above the x minus 2. Since I have an x squared in my second fraction, I need a bx plus c here, because it has to be 1 degree lower. That's the highest possible degree we could have to make these partial fractions. And then we multiply both sides by this denominator. Doing that gives us 7x squared minus 9x plus 11 equals a times x squared plus 3, the part of the common denominator it didn't have, plus bx plus c times x minus 2. Now, the thing to remember here is that this has to be true for all x values. So we can equate coefficients to make a system of equations, but we can also plug in x values to make simpler equations. So I notice here, if I put in x equals 2, that makes the bx plus c part go to 0. In other words, I end up with 7 times 2 squared minus 9 times 2 plus 11 equals a times 2 squared plus 3 plus b times 2 plus c times 2 minus 2. Well, 2 minus 2 is 0, and 0 times anything is 0. So this whole term is going to 0. And now this is a one variable equation just in terms of a. So I end up with 28 minus 18 plus 11 equals 7a. I simplify the left, and that ends up being 21 equals 7a, and a equals 3. Now, I can equate coefficients again, or I can put in another x value and see if that helps. Let's plug in x equals 0, because we love putting in zeros for x's. So the left-hand side becomes just 11 equals a times 3 plus, well, the bx is going to go to 0, so this turns into c times -2. Now, at first glance, this looks like we have two variables, but we know what a is. So I get 11 equals 3 times 3 minus 2c. So 11 equals 9 minus 2c. I can subtract that 9 from both sides. So I get 2 equals negative 2c. I divide by that negative 2. And we have negative 1 equals c. Now, I can put in another x value if I want. I've found that in this case, it's often easiest to equate coefficients because I'll end up with something just in terms of a, b, and c. Or I can get something in terms of two variables. So remember, equating coefficients is where we distribute the a, b, and c. We distribute the right-hand side and simplify. And the first thing I notice is I only have two x squared terms, the ax squared and bx squared. So that means that ax squared plus bx squared must equal the 7x squared. So a plus b equals 7. But since I found that a equals 3, I can plug that into that equation. So I end up with 3 plus b equals 7. So b must equal 4. Now, at first glance, you may think, hey, this means I'm done. Well, not quite. Remember, my final answer is that decomposition. So I have to put everything back into the decomposition. Since a is 3, I have 3 over x minus 2 plus 4x, putting in my b, minus 1 for c over x squared plus 3. And that is our final answer here for the partial fraction decomposition. All right, the last little bit is all Chapter 7 stuff. Now, on your final exam and on this exam, you will have a list of formulas. These formulas I've put right here. Remember, let me take a moment and make sure I don't move this around anymore. These plus ones are all with arithmetic sequences, or in other words, sequences where we have an adding pattern. Whereas these ones with R are geometric. So just know you'll be able to use these formulas on the test. You do not have to memorize them. So let's look at 8. A theater has 45 rows of seats. The first row has 23, the second row is 26, and each of the remaining rows has 3 more seats than the previous row. How many seats are in the theater? I notice here I have a repeating pattern, or an adding pattern. And according to my formulas, when I have an adding pattern, it's going to be my first term plus whatever I'm adding times n minus 1. All right, let me rewrite that a so it actually looks like an a. So we have a sub n equals 23 plus 3 times n minus 1. Awesome. But what's the question asking? How many seats are in the theater? So that sounds like I need the total seats. And so I can go over to my formulas and find the arithmetic total formula. And that's this one right here. So looking at that, it's n over 2, a1 plus an. And so how many rows are there? 45. So let's figure out how many rows or how many seats are in the 45th row. So a45 equals 23 plus 3 times 45 minus 1. I'm going to plug that into a calculator because I'm feeling lazy. So 23 plus 3 times, I guess that's 44. And so that means in the last row, on the 45th row, there's 155 seats. And our sum formula said the sum over 45 rows is going to be 45 over 2 times the number of chairs in the first row, 23, plus the number of chairs in the last row. So that's 45 over 2 times, let's see, 23 plus 55 is 178. Once again, I don't feel like doing that math in my head. I can plug that in a calculator. And that tells me that this theater has 4,005 seats. I don't know if any of you have been to the Hale Center Theater, or I can't remember what the new one is called here in Utah, but it's a wonderful theater. All right, now we're given a geometric expression. Our formulas tell us that a geometric sequence can be defined by the equation a sub n equals the first term times r to the n minus 1. And we call r the common ratio, or the thing that we're multiplying or dividing by to get term to term. And I look at these terms and it looks like I'm dividing by 2, but I'm switching signs. So dividing by 2 is the same as multiplying by 1/2. And since I'm switching signs, it's times negative 1/2. So that means my nth term is my first term, which is 8, times negative 1/2 to the n minus 1 power. So I can multiply repeatedly by 1/2 on the things I have up here to get the ninth term. I can also use this formula. So I have 8 times negative 1/2 to the 9 minus 1 power. And I can go ahead and plug that into a calculator. Now I should note I do like these answers written as fractions. But the nice thing is most calculators these days can convert it to a fraction for you. And so my calculator says that is 1/32. And that makes sense because I have 6 terms here. I'd multiply by that 1/2 3 more times. That negative 1/2 3 more times, that would force it positive. And it'd be like multiplying 1/4 times 1/8. All right, write an expression that could be used to find the sum of the first 10 terms of the geometric sequence. You do not need to calculate the exact sum, just set up the expression. Well, I know that the sum of n terms is a sub 1 times, this fraction can be written in a number of ways. I'll write it like it is on the formula sheet. See, it's 1 minus r to the n over 1 minus r. So I have 1 minus negative 1/2 to the n, or sorry, I'll put the general formula here, 1 minus r to the n over 1 minus r. So the sum of 10 terms is going to be my first term, 8, times the fraction, 1 minus negative 1/2 to the 10th. Now, I've seen people try to pull that negative out. In this case, the negative would go away after it being taken to the 10th power. So generally, I recommend just leave it like this. Just remember that all of r needs to be in parentheses. All of my ratio needs to be in parentheses to show that it's r to the 10th power. And that is a sufficient answer. So I'm just asking you to plug numbers into the formula. But now we'll use it for an infinite series. Now let's first check to see if we can do this. So a sub n, in this case, let's see. My first term is 7, and it looks like I'm multiplying by 1/3 each time. And so we know that this sum exists if the common ratio has an absolute value less than 1. And is the absolute value of 1/3 less than 1? Yes, so we can do this. The formula for an infinite sum is our first term over 1 minus the common ratio. So in this case, that's going to equal 7 over 1 minus 1/3. So that equals 7 over 2/3. Dividing by 2/3 is the same as multiplying by 3/2. And so this equals 21 over 2. And there you have it. That's how we find this infinite sum. Now, use the binomial theorem or Pascal's triangle to expand 2x minus 3 to the fourth. I personally like to use Pascal's triangle just because I like how it looks. Remember, though, that our binomial formula says that a plus b to the n power is the sum from, let me make sure I match the formula here. They use i's here. I equals 0 to n of a to the n minus I power times b to the I power. Notice those powers always add to n. That's a big part of the binomial theorem. Now I'm missing an important part, and that's the binomial coefficient. Didn't leave myself enough space for it. So let me move this over real quick. But my A didn't want to move. Sorry, A, I'm going to erase you. And of course, it erased way too much. So we need my binomial coefficient and choose I. And that's our thing with factorials. Coming up with that can be a pain. So I prefer to write Pascal's triangle unless I'm using some ridiculous high power. The nice part about Pascal's triangle is that I can add rows. I know it's ones on the outside. And then the second entry is always whatever the next number is. And I add the 2 entries above to get the one below. So I got that 6 in the middle because 3 plus 3 is 6. I got that 4, 1 by noticing the pattern 2, 3, 4, and also because 1 plus 3 is 4. Now, what does this tell us? Well, remember the pattern that it's a to the n minus I times b to the I, or in other words, these two powers always add to n. So I'm going to think of this as 2x plus negative 3, because remember the binomial theorem only works with addition, to the fourth power. So my n is 4. So I'm going to use the row that has a 4 starting in it. So I'm going to have 1 times the first thing to the fourth power, and notice that 2 comes along with it because that's part of the first term, plus 4 times, now I'm going to go down a power on the 2x and then bring in a negative 3 to the first power. And now I will steadily bring down the powers on 2x and increase the powers on the negative 3 by 1. I'm using that 14641 to get what we call the binomial coefficient, the number that just comes from what we do when we multiply this out. And so I'm going to add 4 times 2x to the first power times negative 3 to the third plus negative 3 to the fourth power. I guess I should have a 1 out there for the binomial coefficient of 1. Now we get to simplify this, which is a pain, but it works out pretty well. You can use your calculator to help you if needed. I know 2 to the fourth is 16, so I have 16x to the fourth plus when that all comes together, that actually turns into a negative 96 because of that negative 3. So I have negative 96x cubed. And then when that all comes together, it ends up being a positive, I don't feel like doing that math in my head right now. Let's see, 6 times 2 squared times 9 is 216. X squared. Over here, I have 4 times 2 times 27, because that's negative 3 cubed. I guess it would be a negative 27. So that actually ends up being minus 216x. And then negative 3 to the 4th is a positive 81. And that would be my final answer. Now, is that a pain? Yes. It's less of a pain than actually multiplying this out binomial by binomial. So we can use this pattern to help us out. All right, that is it for this review video. I hope it was helpful.